So let's look at, let's start with number 1. Let's see, what type of problem do we have here? What's the question? What's the approximate natural abundance of 63 copper? Based on what? Based on these two abundances, these two isotope abundances. We're saying that those are the only two. Naturally occurring copper occurs in 2 isotopic forms. My guess is it occurs in more than that, but all the other isotopes are minor or even radioactive. So for our purposes, we're gonna stick with these two and try to solve this problem. So think about how is the average atomic mass determined for an element? You take the let's see, 63 copper and 65 copper. Okay. And you take their abundances, which are not given here, and you multiply those times the atomic mass units for each one. And then you add them together. That's a weighted average. So we've got what for this one? The atomic mass of copper is, okay, the average there, okay, we'll put it down here, is 63.55 atomic mass units. So how did we get there? Well, we had a number here and we had a number here. That was the consequence of multiplying these two together. All right, so we're going to have to make some assumptions here. We're going to have to assume that the this one is 63 atomic mass units and that's 65. That's because we weren't given those values, were we? No. And if we're looking for the abundance of 63, then why don't we use a little algebra? Just say that this one is x, some value x. So that means the other one is 1 minus x. If we're going to use fractional amounts, and that's what I prefer. So the fractional amount of this one and that one is like that. Okay. Then we have to multiply that by some value. We're not given the actual atomic mass units for each isotope. You know, since which one is the only one with a whole number? Carbon 12. It's 12 to infinite zeros because that's the established standard. The rest of them are all fractionals, but we're not given that. So we have to use 63 here. And we have to use 65 here. Okay, so this gives us 63x, and this gives us, I'm going to go ahead and multiply these out, 65 minus 65x. And add those together, and that equals this. Okay, so now we have an algebraic expression in one unknown we can solve for it. So let's move this expression up here. Plus 65 minus 65x equals 63.55. Then you just resolve that expression. So this is minus 65, and that's 63x. So that's minus 2x, right? Minus 2x are these two. And then 65, we can take 65 on the other side. 63.55 minus 65. Okay. I kind of skipped a step in there. Did I lose anybody? Okay. Good. Okay. Now this is minus 1.45. Right. We add that to this one. And carry the 145. That's right. So this is minus 2x equals that, and X equals negative divided by negative, 1.45 divided by 2. So 2 into 1.45, where's my calculator? No, I pulled it out. All right, 1.45 divided by 2 is 0.725. 0.725 is the fractional abundance. They're given it in percent, so you just multiply by 100. 72.5%. And the closest one to that, they say approximate. So it has to be this one, 70%. And I bet they're saying approximate because they didn't give us the actual values for these isotopes. All right. So that was one. Next one I got marked as 3. And we can almost see it. I still haven't got my scroll mouse yet. My wireless scroll mouse with a pointer in it. I got my eyes on one. I just have to find the money to buy it. This thing's probably 8, 9 years old by now. Okay, average mass of carbon atom is 12.011. That's what you'll find on the periodic table. Assuming you were able to pick up only one carbon unit, and I assume that means one atom. The chances that you would randomly get one with a mass of 12.011 is what? It's a trick question. That's 0. You will not find one with that mass. Exactly. It's the weighted average. So you'll never find one with that weight. Okay, 3, 4. What's the mass of 4 atoms of copper in grams? Okay, we can pretty much count that one out. There are no 4 copper atoms that are going to weigh that. I suspect what they did was they took the molar mass of copper and multiplied by 4. Just to catch a student that's not paying attention. But the actual calculation requires that we use dimensional analysis, and we say 4 atoms of copper is converted to what? Well, if we're going to grams, the only conversion factor we know for conversion from numbers to mass is the molar mass. So we got to make moles first. We got to cancel atoms and make moles. If we do that, then we can use molar mass to leave us with grams and cancel moles. Like that, like that, like that, like that. So what's the number that goes in here? Avogadro.
6.022 times 10 to the 23rd.
Right. And how about this one? We have to look that one up. What copper is what? 63 something. Rounded off 63.55. I usually round off to 2 decimals. Okay, so that should give us an answer that we can find. Let's see, 4 enter and divide by Avogadro. And then times 63.55. I get 4.22 times 10 to the minus 22. There we go. Okay. That's like I said at the very beginning. Lots of problems. As long as you're kosher with the chemistry, then lots of problems in chemistry are solved by unit conversions. Okay. Skip 5. It must be repetitive. And go to 6. Let's see, can I page? Not enough. There we go. You have a sample of zinc and a sample of aluminum and an equal number of atoms of each. Okay. Which of the following statements concerning the masses of the samples is true? The key here is, well, two keys. One is equal numbers, and the other is different elements. The mass of zinc sample is more than twice as great as the mass of aluminum sample. All right. I can see where this is going. Ratio of the masses, the total masses. So if we've got equal numbers, what is responsible for the difference in masses? That's the mass of each atom, right? So if we ratio the mass of each atom, we should have a handle on where these questions are going. So let's see, what's the mass of aluminum? 26.98, okay. 26.98, and the other one was zinc. Okay. Okay. So what is that ratio? 26.98 and 65.38. That's 0.41. Or the reciprocal of that would be what? Just in case they ask it the other way around. 2.42. So this would be zinc over aluminum. And that would be aluminum over zinc. Just in case. Okay. The mass of zinc sample is more than twice as great as the mass of aluminum. Well, yeah, mass of zinc is greater than aluminum. I think that's the answer. Well, I know it's the answer because I'm using the key. But can I prove it? Right. There's the proof. The others must be false because we don't have any odd answers down here saying one of the above, two of the above, none of the above, all that kind of mess. But the key also is that we ratio the masses of the atoms. Since we have equal numbers of atoms, the difference in the total mass has to be due to the difference in the individual masses of each atom. Let's see. Yeah, want to take a look at 7. Good, it's on there, we can see it. I just don't like a cursor sticking up there in the way. There we go. A sample of ammonia has a mass of 43.5 grams. How many molecules are in that sample? Notice, we don't tell you what ammonia is. And in fact, you don't need to know. I don't think. Oh, yes, you do. Yeah, you do. All right, so I need to tell you what ammonia is. Well, you know what the ammonium polyatomic ion is? Just take away one of the protons. And charge goes with it. Right? So if ammonium is like this, ammonia is like that. Neutral. Okay. So if that's ammonia, we want to know how many molecules are in the sample. Well, first of all, we have to find out how many moles there are. So if we start off with 43.5 grams, we got to find out how many moles there are first. And then we can change moles into molecules. Avogadro again. We need to know ammonia. So nitrogen is 14.01. Hydrogen is 1.01, but we got 3 of them. 1704. There. You guys can do this too, and see if you can do it faster than I can. It's divided into it, and then Avogadro's number. So I get 1.54, 3 significant figures, 15424. 1.54 times 10 to the 24th molecules. Now my guess is that these other answers, I didn't make up these questions. I got them from a test bank. My guess is that whoever makes up the questions, they go in and they say, all right, what kind of mistake could a student make? Say, let's make that mistake, and that's one of our answers. They're devious that way. So just because the answer's there doesn't mean it's right. All right, who's next? Skip down to 11. Here we go. We'll put that one in the center. Calculate the molar mass of barium sulfite. Barium sulfite. So this just emphasizes the fact that you got to, in the first 2 chapters, we learned, actually this was the second chapter, we learned how to write compounds. So if you haven't mastered that technique, you're going to be SOL, as they say. Barium and then sulfite. That this is a -2, barium is a +2 because it's alkaline metal. Alkaline earth, excuse me, alkaline earth. And this is polyatomic with a fixed charge. So you only need 1 of each. Now you just need to add up 1 barium, 1 sulfur, and 3 oxygens. So in the interest of brevity, the answer should be 217.40. All right, who's next? I'm gonna skip down to 17. Let's see if I can page it. Oh, just missed it. 17. This one looks like, okay. I think we have to make an assumption or two with this one also. A compound is composed of an element X and hydrogen. It's going to be this and hydrogen until we're told different. Analysis shows that the compound to be 80% X. So it's 80% by mass X with 3 times as many hydrogen atoms as X atoms. So we got 3 here. There we go. Is that everything we're given? Now the question. Which element is X? What do we need to know to determine an element? We can do it one of 2 ways. The definitive way is atomic number, number of protons. But we can't get protons out of this. There's not enough information. So the secondary way is to find out what's the molar mass of the element. And most elements in the periodic table have significantly different molar masses, so you can tell them apart fairly easily. There are only a couple of places in there where they're so close together that this method would require a tiebreaker of some kind. Like, let's see, for example, let's see, it's right down in here somewhere. Iodine, tellurium, maybe antimony, tellurium. They're about 4/10 difference. No, I'm looking at the wrong number. I'm sorry. Here we go. 121. Yeah. Tellurium and iodine are very close. They're within 0.7 atomic mass units of each other. So in that case, iodine is, let's see, tellurium, iodine. I'm just going to go for phases, but they're both solids. Anyway, you'd need a tiebreaker of some kind. All right, let's get back to the problem. So if it's 80% X, how much is hydrogen? 20%, right? That means it has to be 20% hydrogen. And if we're going to try to find out what X is, we've got to go for molar mass, which means we need a mass for X, and we also need how many moles of X. So let's use that same trick as we used in determining empirical and molecular formulas, right? Percent parts per 100. Let's just say we have 100 grams. That means we have 80 grams of X and 20 grams of H, right? So if we say 100-gram sample, now we have 20 grams of, let's see, is that extras? That's 20 grams of hydrogen. So let's find out how many moles of hydrogen are in that molecule, because we know the ratio of X to hydrogen. So if we find out the hydrogen is 1.01 and 1 mole, how many moles of hydrogen does that represent? 20 divided by 1.01. You could probably round it off to 1 and just say it's 20. But I've got 19.8 moles of hydrogen. So if there are 3 times as many moles of hydrogen as X, we just divide this by 3, correct? And we find out how many moles of X we have. Or you can use dimensional analysis, just do it like this, say like that, moles of hydrogen, moles of X, and the ratio is 3 to 1, right? So that one cancels. So we divide 19.8 by 3. 6.6. So we actually have 6.6. Hold on a second. Let me write it like this. 6.6 moles of X. So how many grams does that represent? Well, if this was 20 grams to give you that many moles, that one's 80 grams, right? 80 grams of X. So what is that? I already got 6.6 in the calculator, put it in 80. 12.12 grams per mole. Then you just go to the periodic table and look. Closest one to that one is carbon, 12.01. Right, so what do we have here? We've got a pretty good bit of experimental error, like 8 or 9% error. So the key to that one is to recognize how. Where are you headed? How can you determine an element if you don't have the number of protons? Your next best bet is molar mass. And then you hop on your horse and ride. Use the data you've got to find the mass of X and the moles that represents. So that was a multi-step problem, I guess you could say. What's next? That was 17. 19. Oh, there we go. That's good. Okay, substance contains 35 grams of nitrogen, 5.05 grams of hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in a 153 gram sample? Okay. So Who do we owe this one to? Robert Proust. The law of definite composition. It's going to be that composition forever and always, no matter how much you have or where it comes from. If you have, what is it, 35, 505, and 60. 35, 5.05, and 60. So that's 100.05 grams total. 100.0, let me write it down here. 100.05 grams, that's total mass. Okay, which one are we getting at? Hydrogen. So what's the percent? Or even just the fractional amount of hydrogen will do, 5.05 grams of hydrogen for that much. Right? And if the ratio is constant, then we can set this and find out what the new mass of hydrogen is if we have a larger sample. Right? That ratio is constant. So this one has to be equal to that. So now all we have to do is multiply 153 by 5.05 and divide by 153, 5.05 times divided by that. See, like this. There we go. 7.72. So X equals 7.72 grams. There it is. Okay. We didn't even have to overthink that one, did we? Let's see. Next one, I skipped a bunch of them. There's a lot of repetition, obviously. 32. Let's see if I can page down to 32. Good. Empirical formula of styrene is CH. Right, so what's the empirical formula? The simplest whole number ratio of elements, correct? And it has a molar mass of 104.1. So that is the mass of the actual, the molecular formula. So what are we looking for? Well, if this is the empirical, we're looking for that multiplier. It propagates through all the subscripts and gives us something over here. Well, we know that this something over here is 104.1 grams per mole. If X is 1, then that's the formula. But if X is a multiple, then, so how do you approach this? Well, you find what I call the empirical weight, or the empirical mass. So that would be 12.01, right? And 1.01 for hydrogen, 13.02. So now, if the ratio here depends on that multiplier, then ratio this to this should give you that multiplier. So we should divide this one through by 13.02. Find out what that multiplier is. 104.1 and 13.02. Nearest whole number, 8, approximately 8. So the formula then is C8H. 8. Right here. I'm not sure what that is though. It could be a cyclic compound, or it could be, I don't know. I'm not familiar with that one. This one, yeah. That one's benzene. I bet my neighbor's last dollar on that one. Okay, 32 and 33. Let's see. Yeah, that's not going to do. No. Chop it off. 33. Okay. Come back around. Let's see. Yeah, 33. Adipic acid contains 49.32% carbon, 43.84% oxygen, 6.85% hydrogen by mass. What's the empirical formula? So they don't even make us go all the way to the end. You just go to the empirical and that's the answer. So you remember how to do that. Keep leaving it down there in the way. Well, I set up an assembly line like Henry Ford. We're going to have 49.3% carbon, 43.84% oxygen, and 6.85% hydrogen. That should add up to 100%, or pretty close to it. It's almost 50, with this probably left over. Yeah, it's probably good. But we're faced with the dimensionless number problem again, percent. So we have to assume, just for argument's sake, that we've got a 100-gram sample. If you do, that means this becomes, save myself some writing, this becomes grams. The ratio is exactly the same. Now we can convert it to moles. Why do we need to do that? Because empirical formulas and molecular formulas, they're all based on numbers of atoms, not on mass. So we got to find that, but that ratio is already fixed. So if we determine the number of moles of this one, that one, and that one, the ratio is still the same, whether it's moles or mass. So we just need to convert this 12.01 grams, 16 grams. Yeah, get out of the way of the camera so you can see me working. 1.01 grams. Okay, that's moles each. Here we go. So now we just need to do a little ciphering. 49.3 divided by 12.01, which is 4.10. Yeah. 4.10 moles, and 43.84 divided by 16 is 2.75. 4 moles. And hydrogen, 6.85 divided by 1.04 is 6.78. 6.78 moles. Okay. Now we have the molar ratio. We just don't have the whole number. It would look funny if we wrote it like that. 2.74. I mean, technically it's true. That's the ratio of moles, but that's not the ratio of atoms. So we need a whole number. So how do we get the whole number out of all this mess? Well, first step is divide everything through by the smallest one. Right? Why not the largest one? Because if we use the largest one, some of them will be fractions. We want to come at it from underneath. No, from overhead. Whole numbers. And we can do that because mathematical rules say if we do the same thing to every one, we haven't changed the ratio. This obviously is going to be 1. 2.74 into 678. 4 is 2.48. 2.48. This one is 410 divided by 2.74. 1.50. Okay, we're almost there. Now, this one is pretty close to 2.5. That one's exactly 1.5. So how do we get rid of a half? Multiply by 2. We multiply by 2, each one. This one is 3. This one is 2. And this one is 5. So there's our empirical formula. COH. C3O2H5. Okay. They switched the H, put the H in front. That's okay. So it's C3H5O2, this one right here. It's okay to do that if your formula does not have a polyatomic in it. If there's a polyatomic in there, don't split it up. In other words, if we had nitric acid, it just wouldn't do to write HO3N. It loses its meaning when you do that. So polyatomics need to be, you got to keep the elements in order. All right, that was 33. And I'm going to skip down to 40. If I can page to 40, that would be great. There it is. What's the sum of the coefficients of the following equation when it's balanced using the smallest whole numbers? Okay. So what do we have to do? We have to balance the equation, right? Well, let's see. Let's see if we can use a trick. Are there any polyatomics there? There's one there, but it's not over here. So we're going to have to use individual atoms in our budget. Yeah, I mean elements. So let me go where I've got more room. Let's see. Instead of trying to do it under here, that squash it together to do that. So let's write. What is this? Let's see. NH2 is sodium amide, sodium nitrate, sodium nitride, sodium hydroxide, and ammonia. Okay. I think I need a new marker. That was given out on me. I just happen to have a backup supply. Let's see, sodium. Let's do it right here. Okay. And then let's leave ourselves a space for coefficient here. Nitrate. And that yields sodium. Oops. Broke my own rule. Move it over a little bit. Sodium nitride. Sodium hydroxide. And ammonia. Okay. We balanced using redox method. I think we did at the end of chapter 4. I'm wondering if that might be a better approach to this one than just trying to brute force it through on elements alone. Let's see. All the sodiums are +1, so they didn't change oxidation states. This one would be +2, +1, so this one would be -3. for that nitrogen. How about this one? Well, if we look at nitrite by itself, we have -2 times 3 is -6. Hold out 1 for that -5, so that's +5. I'm not so sure this is the best idea because you don't know which nitrogen went where. All right, so I'm going to take a chance. Let's see if we can do this without oxidation. Redox. Maybe we can, maybe we can't. Sodium, nitrogen, hydrogen, oxygen. Be good to everybody. Okay, on this side we have 2 sodiums, 2 nitrogens, we have 2 hydrogens, and we have 3 oxygens. Sometimes you can do it without redox. I'm hoping I can. 1, 2 sodiums, nitrogens, 3, 4. Hydrogens, 1, 2, 3, 4. And oxygens, 1. Okay. We don't have any simple elements. Do we have any with the fewest number of elements? This one. So it's kind of a corollary to if you have a free element, save it to last. Try to save this one to last because it only has 2 elements. Trouble is, nitrogen's here and there. Okay, so where are we uneven? Here, here, and here. I don't know where to start is best. So how would we get 4 nitrogens here? Well, we could put 4 in front of that one, but we could put 2 here and 2 here to get that one. What about oxygens? Oxygen's only one place here, and it's only one place there. Let's try that one first. So 3 here would give us 3 oxygens. It would give us 3 sodiums. 1 sodium is 4 sodiums. Okay. And nitrogens. Nitrogens, hydrogens. Nitrogens are 3. No, okay, that didn't change. Oxygen. That's 1. We did that one already. 3 hydrogens. 3 hydrogens, 3 hydrogens, 6 hydrogens. Okay. All right, so we still need 4 sodiums on that side. We need 4 nitrogens on this side. What if we do that? 2 here and 2 here. What'll that do? Probably messes us up pretty good. 4 there and 4 there. Okay. That also changed the nitrogens. 2 nitrogens and 2 nitrogens is 4. Oh, okay. So that got us 4 nitrogens. And 4 hydrogens. 4 hydrogens. And oxygens. Did it change oxygens? 6 oxygens. Now I'm going to try one more move and then we might have to go to redox. We got 6 hydrogens here. We'd need 3 on this side. That's no. It's going to take forever. All right, we're going to have to do it redox. And it looks like it's going to take some assumptions of some kind because this fact, if this is +1, this is +1, plus 1 plus 1. This is plus 1. So that means this nitrogen is minus 3. This one is plus 1, oxygen's minus 2, hydrogen has to be plus 1. This nitrogen, since that's a plus 1, this one has to be, oh, how do we do that? Did I write that correctly? Oh, looking at the wrong one. Okay. Sodium nitride. Yeah. So this would have to be a minus 1/3. Right? To balance it. How do you do that? All right. I'm going to have to go. How did I solve this before? So let's do our tally again. Sodium, nitrogen, hydrogen, and oxygen. So we got 2, 2, 2, and 3. Right? 2, 2, 2, 3. On this side, we have 2, 4, 4, and 1. 2, 4, 4, and 1. Is that right? 1 oxygen, 4 hydrogens, yep. 4 nitrogens, yep. And 2 sodiums. Okay. First step. This one. What am I trying to do here? Can't be for sodiums. Oxygens. Yeah, that's what I did before, wasn't it? Put a 3 there. So that gives us 4 sodiums. And still 4 nitrogens. 3 oxygens. Maybe I counted wrong when I did it the first time. I bet that's what happened. 3 hydrogens, 6 hydrogens. Okay. Nope. Looking at the wrong one again. 2, 4, 4, 1, 4, 6, 3. Okay. And then we're saying all we need is a 3 over here. If we put a 3 there, that'll make 4 sodiums. Yeah. That'll make 3 nitrogens, 1, make 4 nitrogens. Can't be that simple, can it? 6 hydrogens, 3 oxygens. I was obviously overthinking. Yeah. Okay, so let's answer the question. What's the sum of the coefficients? All right. You got 1 here, 3 plus 1 is 4, plus 1 is 5, 6, 7, 8, 9. There you go. Well, I just blew the rule of thumb out of the water. It's supposed to take the instructor 1/4 of the time a student to work a problem. So my only out here is that the student tried to work that one and just threw their hands up. So that's infinite time, and 1/4 of that is whatever I want it to be. Okay, 40, done and gone. 45. 45's got a picture. There we go. Chemical reaction has 2 A's plus B yields C, which of the following figures best illustrates the stoichiometric ratio of A and B. All right. Look at the question. Which one best illustrates the stoichiometric ratio of A and B? So they're saying that the reaction hadn't even occurred yet. Which one is the stoichiometric ratio of A and B? 2 A's and 1 B, ratio of 2 to 1. So let's look at this one. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Well, there it is right there. 2 to 1. Oh, but it could be more than one. Okay. So if we know 1 is the answer, let's look at 4 and see if it fits. Oh, no, it's got C in it. Can't be it. So it has to be this one. If you look at the others, you'll find the ratios are all wrong. That's the whole point of that question. 46. Let's see. I need to scroll that one. I forgot to fix this. Okay. There we go. Yeah, that cart is a wide berth. "46. 7.11 grams sample of potassium chlorate was decomposed according to the following equation. How many moles of oxygen are formed?" Well, this is obviously a stoichiometric problem. And it's simple to decompose potassium chlorate. Just stick it in a test tube and heat it. And it will spontaneously, with a little heat, will decompose into potash and oxygen. So how many moles of oxygen are formed? Let's see, is this one balanced though? 2KClO3 yields 2KCl plus 3O2. 6 oxygen, 2 Ks, 2 chlorines. Yeah, it's balanced. So they're saying we're starting off with 7.11 grams of that material. How many moles of oxygen are formed? All right, remember the rule. Once you balance your equation, you can't go anywhere in that equation unless you're moles. So mass cannot stand. We have to convert this to moles. And grams cancel, leaves us with moles. We need potassium, chlorine, and 3 oxygens. Potassium is what? 3910, rounded off. For potassium, chlorine, I know that one, 3545. And 3 oxygens is 48. 3 times 16. Okay, so that's 5, 5, 14, 22, carry the 2, 6. 6 is 12. 122.55. Okay, divide that into 7.11. 7.11, 122.55. Okay, I get 5.80 times 10 to the minus 2. 5.80 times 10 to the minus 2 moles of potassium chlorate. Okay, how do we find the moles of, which one was it? Oxygen. We need a conversion factor. Where do you get your conversion factor now? From the coefficients. The ratio is 3 oxygens for every 2 potassium chlorates. So now we have divide by 2 and multiply by 3 on that number. I get 8.70 times 10 to the minus 2. Yeah, 8.70 times 10 to the minus 2 moles of O2. But we're in standard notation, so I got to say, all right, 2 places. Move it over here. 0.0087. There it is right there. Okay. Let's see. skip down to '64. There we go. The reaction N2 plus H2 yields N2H4. If the percent yield for this reaction is 82%, what's the actual mass of hydrazine, which is this, hydrazine, produced when 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen? Okay, this is obviously multi-step. The one step that's the one step that's already done for you is the balance equation. So, let's see. I guess we'll put it down here. So 2H2, no, N2 plus 2H2 yields N2H4. What are we given? All right, let's extract information from the problem. The question is, what's the actual mass of hydrazine? The actual mass. The percent yield for this reaction is 82%, which is really pretty good. And we're given 25.57 grams of nitrogen. 25.57 grams of nitrogen. Reacts with 4.45 grams of hydrogen. Okay. So now we've got it removed from the confusion of the word problem. We can see that to answer the question, we just need to find out what's the stoichiometric mass of N2H4 and then apply our yield factor. So whenever you're given two or more values for reactants, in this case there are two, so if you're given values for both of them, you can be pretty sure that one of them is going to run out first. We got a limiting reactant there somewhere. So how do you find the limiting reactant? Because the limiting one is the one that's going to determine the theoretical 100% yield for this one before you even apply that value. Well, you find out how many moles this will produce here and how many moles this will produce here. And the one that produces the least number is the limiting one. So we need right number of moles of this one. So N2 is what molar mass? 14.01 times 2, 28.02. So I'm going to shorten the 28.02. And that produces how many? 2557. 25.57. And 28.02 is 0.9126. 0.9126 moles of nitrogen. How about this one? Hydrogen would be 2.02, correct? That one makes 4.45 divided by 2.02 is 2.203. 2.203 moles of hydrogen. Now we just convert. This is 1 to 1, right? One here, one there. So we know that this one is 0.9126 moles of hydrazine. Okay. And this one, well, it's 2 to 1, so this one's going to be half of that one. So that's going to be 1.115. Wait a minute. 015 moles of hydrogen. Right? I just took half of this one because the ratio is 2 to 1. So half of that is this. All right, so this is the limiting one, right? That means we're only going to have this many moles of hydrogen. So what's the mass of hydrogen? Because before we apply this, because this is written in terms of mass, we need grams per mole. That means we need the molar mass, the grams on top. So 1401 times 2 is 2802. And then 4 hydrogens, 4.04, is 3206 times 0.9. Let's see. That. How to work this thing. It's multiplied by that. Yep. Okay, so I can get multiplied. 2.9, 29.3. 29.3 grams. Now we can apply our correction. So you can use percent as long as you get rid of 100, but I like fractions. Times 0.82 is what? 24.0. All right, that should be up there somewhere. Right here. Okay. All right, that was 64. How are we doing on time? We're about to the end anyway. 71. Here we go. Naturally occurring iron contains 5.82% of this isotope, 91.66% of that one, 2.19% of that one, 3.33 of that one. The respective atomic masses are for that one, for this one, for this one, for this one. Calculate the average atomic mass of iron. That's pretty simple, actually. If you take this times 0.0582, that's this isotopic contribution. This one times 0.9166. This one times 0.0219. And this one times 0.0033. 0.0033 times this one. Add them together, and you should get that value. Okay. Let's see. How about okay, I'm going to come back to 72. That one takes a little doing. Let's get these. Wait a minute, that was only chapter 3. Still got chapter 4. All right, let me check the time. When does our lab start? 11:30? 11:30. Okay, so we got an hour. All right. Oh, this is unit conversion, dimensional analysis. That's all that is. If we have time, we'll come back to it. All right. How about this one? Let me scroll up a little bit, see if I can get it all on the page. everything on the screen. Now, give the empirical formula for the following compounds. You don't, well, first step is you count up all the individual atoms of the elements, right? 6 of these and 6 of those. But then the empirical is you have to simplify it to the whole number, smallest whole number. So if this is C6H6, it has to be CH is the empirical. The second one is C2H4. You can only simplify that one down to CH2, dividing everything by 2. This one is a little messier. All right, let's see. There's 1, 2, 3, 4, 5, 6 carbons. I better put that one up there. I forget. So the empirical, the molecular formula is C6 H what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. H12 and O what? 1, 2, 3, 4, 5, 6. You know what that is? Glucose. And to simplify it, it looks like you can divide everything through by 6. So it'd be 1, 2, and 1. Let's see, and one more. All right, this one is 1, 2, 3, 4, 5, 6 carbons and hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens and 2 oxygens. So it looks like you can divide everything through by 2. Yeah, because this one will be 1. It'll be 1, 5, 3. Trying to see what is that molecule. Methyl 6. I'm not sure what that one is. Okay. Let's see. Epinephrine. Percentage composition, determine the empirical formula. Okay. We've done one of those before. Empirical formula. You just set up your assembly line and bulldog it through. Okay, chapter 4. Okay, chapter 4. And I'm going to skip all the way to number 12. Not going to let me. There we go. How many grams of sodium chloride are contained in 350 milliliters of 0.287 molar solution of sodium chloride? Okay, molarity. Go back to the definition. Moles per unit volume. Volume has to be in liters. How many grams of sodium chloride are contained? 300. Let's see what the volume we're given is 350 milliliters. The molarity is given as 0.287 molar. And the question is, how many grams of sodium chloride do you have? So what's the mass? Okay. We can't take a direct route. We can find out how many moles of sodium chloride that is. Sodium chloride. But we have to convert this to liters first. So we move 1, 2, 3. 0.350 is the volume. 0.350 liters, and molarity is 0.287 molar. So if we multiply this one times that one, we should get moles. That's our first step. 0.35. So I get 0.10045. 0.10045 moles of sodium chloride. Now we can convert that to grams. We just need molar mass of sodium chloride. So what's sodium? 23. Yeah, 23.00. Chlorine, 3545. Is 58 value. So we want to multiply that by 5845. And I get 5.87. There it is, 5.87 grams. Oh, sorry, sodium chloride in that solution. Suppose we wanted to recover that sodium chloride. How could you do it? Simplest possible way. It's in solution, right? So you can't filter it. Evaporate it, right? Just boil it down, because sodium chloride is not volatile. So you can bring the water up to, of course, the boiling point of water is going to, as you'll reach saturation at some point as the water decreases in concentration, in volume. Then you'll start to see it drop out. And then at that point, when the water is saturated with sodium chloride, it'll be at its maximum boiling point. Speaking of which, hold on a second. Let me do something with that Jessica before it sucks up all the water from the roof. Let me just put extra. Not perfect, but it should suffice. Let's see. All right, where was I? Number 12, we finished number 12. Uh, 14. Okay, 14, as luck would have it, is on the board. What mass of calcium chloride is needed to prepare 3.950 liters of 1.49 molar solution? Okay, we go back to our definition. We want to know the mass. So if we can't get there directly from here, what we need is moles of calcium chloride. And if we look at the formula, right, we need moles is just molarity times volume. So we take this molarity times volume. .950 liters. That gives us so many moles of calcium chloride. Let's see, 5.886. 5.886 moles of calcium chloride. Then we just need to convert that to mass. Moles on the bottom, grams on the top. Calcium chloride. Calcium is close to 40, I think. 40.08. So 40.08 for calcium, and then 2 times 35.45 for chlorine. Okay. 5 times 2 and then 40.08 is 110.98. 110.8. So multiply that times 5.886, which should still be in the calculator. 65.32. See, three significant figures. 65.3 grams. No, that's not right. Yeah. I misread something. Hold on a second. 1.5. Yeah, that's right. Moles. Oh, 653. 653 grams. There we go. That's it right there. 653. Okay, when the calculator spits out answers in scientific notation, try to do that in your head, converting backwards. It's a challenge. Okay, that was 14. 18. Almost. Well, actually, I did get it, didn't it? Yeah, we only have A through E. What volume of 18 molar sulfuric acid must be used to prepare 2.3 liters of 1.145 molar sulfuric acid? This is a dilution problem. Concentrated, concentrated, diluted, diluted. So which is which? Concentrated is 18 molar. And the question is, what volume of that 18 molar do you need? We know that much. What's the molarity of the diluted solution? 0.145. And what's the final volume of the diluted solution? 2.30 liters. Okay, now we'll solve for it. What volume? And the volume is going to be in liters. Don't forget that, liters. And the answer they're looking for is in milliliters. So we need 0.1145 times 2.3 and then divide by 18. So that's 1.85 times 10 to the minus 2. Or, let's say, that would be 0.0185. So it's 1, 2, 3, 18.5 milliliters. They're going to restrict us to 2 for the answer. So it's 19 milliliters. That's the best answer out of that group. Let's see. Let's skip down to let's look at 26 through 29. Those are all identify the reactions. What did I say? 26. First one is 26. There it is. And we have to scroll a little bit. Well, let's just scroll a lot. There we go. So what types of reactions do we have here? Well, let's see what our choices are. Acid-base reaction. Are there any acid bases up there? There's an acid. There's a base. Yep, we got acid base. So, acid base is one. Unbalanced reactions. What do you mean by that? There's one there, two, no. They're not all unbalanced, so it can't be B. How about precipitation reactions? Do we have any precipitations? Lead iodide. I bet that is a solid. So we need to, well, you would have to, I know what the answer is. To go on our chart, go across to lead, and then go down to iodine. Yep, just as I suspected, it's a solid. So this one is a solid, which makes it, this is the net ionic equation for that reaction. A lead is going to have a counter anion, and the iodine is going to have a counter cation that will appear on this side if we put them back in there. That's the net ionic equation. So this one is true. This one is true. How about redox? Are there any redoxes in there? Acid-base reactions are typically not redox. And if you run the oxidation states on all these elements, you'll find that's not. How about one of these? That one is a redox, right? Cerium 4+ and cerium 3+. Right? Plus, this one is an ion here, and it's 0 there. So yes, redox. But is that respectively? Precipitation? Yep. Acid-base? No. Not in that order. Precipitation, redox, acid-base. This is it. Okay. Since it required you to put them in order, that's what respectively means. Then you know they're there. It's just that the choice is between this one and that. And this one is the proper order. Okay? That's the devious part about this problem. Okay, 26. 27. The following reactions. Okay, we got another respectively in here, right? So we got to watch the order. So what's this first one? Notice that you've got an element here, an element there, and you're in a compound here. That's a redox. Right? So it's got to be this one or this one. Is this a precipitation? Aqueous, aqueous, solid. Yep, that's precipitation. So it's probably this one. And this is an acid base. So it has to be B. Okay. 28. I know that's get chopped off if I run a page up. So let me scroll it. And no. So how about I do it like that? The following reactions are examples of, okay, now we know it doesn't have to be in order. So are they both oxidation reductions? Let's see, this is aqueous solution, aqueous, aqueous, and a solid. This is a precipitation. Also notice that to start with, it's going to be a double replacement because you got a cation, anion, cation, anion. Now this cation is swapped with that anion, and that one is swapped with this. That one is insoluble. So that's a precipitation reaction. How about this one? That one's also precipitation. Two solutions here, solid there with your spectators there. So oxidation, reduction, precipitation right here. That's the only type in selection. 29. Okay. All the following reactions can be classified as. All right, so we got choices of A and B, A and C. So we got to do all of them. What is this? Oxidation reduction, element, compound. Element comes from a compound. That's oxidation reduction. This one is a combustion. That's automatically oxidation reduction. So they're all oxidation reduction. One of them is combustion, but they're not all combustions. So the only one that gives that the complete answer is oxidation reduction only. Let's see, is that far as I was going on this one? Yeah, down to 29. I want to do 30 also. Let me scroll up and get 30. You have exposed electrodes of a light bulb in a solution of sulfuric acid, such that the light bulb is on. Well, that makes sense. Sulfuric acid and water dissociate. It's a strong acid. Makes mobile ions, so we can light the light bulb with our electrode in sulfuric acid solution. You add a dilute solution, and the bulb grows dim. So we're going to add a solution, and the bulb grows dim. So what does that mean? If the bulb grows dim, we're removing ions from solution. In other words, we're removing those mobile ions somehow. Which of the following could be in the solution? So, do we have any hydrogen-based compounds that are going to be insoluble? No. Acid, you know any acids that are insoluble? Let's look at our chart. Is hydrogen on there anywhere? No. Okay. So whatever reaction we're talking about has to be with the sulfate. Okay. So let's see, what could it be? Well, let's see. What if we added barium hydroxide to that solution? What would the reaction be? Acid base, right? And barium sulfate is insoluble, which look at your chart. So that would remove sulfate, but how about the protons that are floating around there? They react with the hydroxyls and make water. And we all know that pure water is an insulator. It will not conduct. So that's the most likely one right there. We get rid of the sulfate with the barium and get rid of the hydrogen with the hydroxyls. Sodium sulfate is soluble. Nitric acid makes ions. So they're all ions with this one. Nothing's going to happen with that one. How about this one? Nitrate? No. Copper sulfate is soluble. Right? Copper sulfate. Yep. Copper sulfate is soluble. So the only one that works is barium hydroxide. Right. That's why when they do what do they call it? A barium enema. They use barium sulfate as a barium enema because it's not soluble. So your body's not going to absorb it. So it's safe to use. Plus, barium is a massive atom, a massive metal atom, and it shows a great X-ray shadow of your colon. So that's why they pump you full of that stuff, barium sulfate, before they do the X-rays. All right, let's see. Well, I didn't check which one I was going to, did I? 30. Next page. Oh, skip that page. 30. Okay, 38, 39, and 40. They're all based upon the same bit of that information. 38, 39, 40. Okay, we're starting off here with aqueous solutions of barium chloride, silver nitrate are mixed to form solid silver chloride and aqueous barium nitrate. The balanced molecular equation contains which of the following terms? So you basically have to write the equation, balance. Barium chloride. right? So that's 2 plus, 1 minus. This is aqueous. And then silver nitrate. Plus 1 minus 1. That's aqueous. And it forms solid silver chloride. This is a precipitation reaction. Silver and chloride together are insoluble. And then what's left? Barium nitrate. So that needs 2. This is a minus 1, that's a plus 2. And this one is soluble. And now we got our equation written. We need to balance it. Most of these double replacement reactions are fairly easy to balance, even without doing the budget. You just say, we got 1 barium on both sides, good. 2 chlorides, we need 2 chlorides here. Now we got 2 silvers. 2 silvers. That gives us 2 nitrates, 2 nitrates, we're done. Okay. Okay, so the balanced molecular equation contains which of the following terms? This one, it looks to me like they're interested in also the coefficient. So if you think it's this one, then you're wrong because it doesn't have the coefficient. This one does. How about that one? Nope, that one doesn't have that coefficient. Barium nitrate. You okay? Nosebleed?
Yeah.
You need some ice?
No,
Okay.
that's all fine.
So that one doesn't match because the coefficient's wrong. Barium, that one doesn't match because it needs 2 nitrates, and that one's got too many. Okay. So this is the only one that works. 2 AgCl for solid. The balanced complete ionic equation contains which of the following? Right, so now we have to break it up. This is aqueous, so it has to have barium 2 plus, 2 chlorides, right? Aqueous.
What is the back?
It's down the hallway and first hallway to your right before you get to the top of the stairs. Just keep going to your right. Two silvers. And 2 nitrates. Okay. That's the reactant side. The product side is 2 silver chloride solid. Can't change that one. But we do have spectators over here. Barium 2 plus, aqueous, and 2NO3 minus aqueous. Okay, the complete ionic equation contains which of the following? All right, does it contain this one? 2 barium 2 plus? Nope. What about this one? Chloride, single chloride? Nope. 2 silver? Yep, there. 1 nitrate? No, it's 2 nitrates. And silver chloride aqueous? Nope. So this is the only one that works. Right there. How about the net ionic equation? I'm going to have to scroll up for that one. Here we go. Oops. Let's see. There we go. The net ionic equation. So we get rid of the spectators. So we got barium and nitrate. Barium, nitrate. Now we have just the silver, the chloride, and the silver chloride. Now, notice what's happened here. With the net ionic equation, 2, 2, and 2. That's not the simplest form. So the simplest form would be to change those each to 1. Now we have one chloride, one silver, yields one silver chloride. That's the trick in that. So we do have silver plus here. We don't have barium, we don't have nitrate, we don't have hydrogens. We never had hydrogens. And silver chloride, aqueous doesn't exist here.
How do you know which one's respective?
They're on both sides of the equation in the same form. For this one, it shows up over here, all right, but now it's in a solid. It's not aqueous anymore. But this one is aqueous on both sides. This one is aqueous on both sides. Those are spectators. All right, let's see. Skip down to 46. Got a half hour left. Let's see if I can get this done. 46. No, oops, too far. Nope, I'm gonna have to scroll. Keep an eye on my watch and see how long she's gone. She doesn't come back another 10 minutes. I'm gonna have to send you after. What did I say, 46? Yeah, we're going to look at 46 and 47. If all the chloride in 3.734 gram sample of an unknown metal chloride is precipitated as silver chloride with 70.90 milliliters of 0.2010 meg molar silver nitrate, what's the percentage of chloride in the sample? Okay. We're working with a precipitation reaction that's used for analysis. And we still need the balanced equation. Get that out of the way. Here we go. So the reaction that's going to take place, we've got a metal chloride in solution. Some metal chloride. Let's do this. No, because we're using molarity, I better use X. Some metal chloride. And we don't know what the ratio is yet. And we're going to add silver nitrate solution. And it's going to yield the silver and the chloride as a solid. And then we'll have the metal combined with the nitrate. Okay, probably aqueous solution. This is aqueous also. See, I don't know what this is right down here. But it doesn't matter. Because the ratio that we want is here and here. We're getting at this one through the chloride that's attached. So if all the chloride, that means the chloride is limiting. The chloride salt, the XCl is limiting. We're going to use it all up. All the chloride in 3.734 gram sample. 3.734 grams. We do know that. That's the mass of that sample. Is precipitated with 70 point. So what we actually did was a titration. Okay. We added a known amount of silver nitrate of this concentration. So we used 70.90 milliliters of 0.2010 molar silver nitrate and converted all of the chloride to here. So what we need to know is, let's see, what is the percentage of chloride in the sample? We need to know mass of chloride per mass of sample. right? That's what we're getting at. Times 100. So we know what the mass of the sample is right here. 3.734. We need to find the mass of the chloride. So how to get at it? Well, that chloride mass is the same as this chloride mass. So if we find out how many moles here, then we can find out how many moles there and use that to get at the mass of the chloride. Okay, that's where we're headed. So this times this would be millimoles, actually, 70.9. 70.9. And 0.2010 is 14.25. 14.25 millimoles of silver nitrate. Okay? So how many millimoles of this? Exactly the same. It's 1 to 1. Oh. Yes. Actually, we have to assume that. This is millimoles of silver. That's how we get at it. Silver nitrate, this is also millimoles of silver. So we have this many millimoles of silver over here, 14.25 millimoles. Which means we also have 14.25 millimoles of chloride. Okay? So that means that we have this many millimoles of chloride coming from here. Or how many moles is that? 0.01425 moles of chloride. So now we can convert that using 3545 grams per mole. So 0.0125. Let's see. There we go. 3545 is 0.505. 0.505 grams of chloride. So the mass of chlorine here is 0.505 grams divided by 3.734. Times 100 is 13.5%. Which one comes close? This one right here. Did I lose anybody? Okay, good. So sometimes I get the feeling that stream of consciousness is always the best way to solve a problem, but sometimes it works. I just have to know, where am I headed? That's what this said to me. I need to know the mass of that chlorine. So what do I have up here that can get me there? Well, I know the moles here, and that means the moles here are known, which means the moles of that's known. Okay, I'm good now. I know the moles of chloride, I can go from there. Okay?
Yeah.
We're about to send the cavalry. A female cavalry, of course.
Happens all the time.
Do you take blood thinner?
No, I just get it from my mom. She does look no sleep a lot. I don't sleep a lot.
Oh. Okay.
My dad does.
Blame the mom. Okay, 40, that was 46. 47. Let me see how many we got to go. Yeah, actually, there are a few. We should be good. 47. You have 88.6 milliliters of 2.5 molar solution of sodium chromate. You also have 125 milliliters of 2.50 molar silver nitrate. calculate the concentration of sodium after the two solutions are mixed together. All right, what reaction is actually going to occur? Sodium chromate. Aqueous. That means you have sodium ions and chromate ions. We're mixing it with silver nitrate. Right? All nitrates are soluble. So what does that give us? Well, double replacement, silver and chromate together. Silver, chromate. Chromate's a 2- ion, so we need 2 silvers. And to look it up, you'll find that this one is the precipitate. It's insoluble. And then we have sodium nitrate, which is soluble. Okay. Do we need to balance? Well, we can. It'll happen pretty quick. 2 sodiums, 2 sodiums. 2 nitrates, 2 nitrates. 2 sodiums, 1 chromate, 2 silvers, 2 silvers, and 2 nitrates. 2 nitrates. Okay, we're balanced. Now, what are we given? This one is 88.6 milliliters of 2.5 molar solution. And this one is 125 milliliters of 2.5 molar solution. All right. And the question is, what's the concentration of sodium ions after the 2 solutions are mixed together? All right, don't overthink this one. What's the net equation? It has this ion and that ion in it. Everything else is spectators. So sodium's a spectator, nitrate's a spectator. So the sodium you start with is all of the sodium is still in solution. So the only factor that you need to take into account is dilution. Right? How many moles of sodium originally were here? Well, let's say millimoles. That would be quicker. 2.5 times 88.6. So that's 221.5 millimoles. 221.5 millimoles. Okay. That's the moles. What's the volume? If we do the volume in milliliters, then we can divide these two. The milli cancels. So we have 88.6 and 125. 88.6 and 125 is 213.6. 213.6 milliliters of solution now, with 221.5 millimoles of sodium. Right? Milliliters cancel, so we have moles per liter. That's good. Let's see. I was just checking my order here, so I can just hit the divide button. 1.04. Molar. Wait a minute. What did I do wrong? Anybody see my mistake? I do. You got it?
The moles and liters of the block.
Let's go further back from that. Look here. 221.5 millimoles of what? Of the compound. So that means twice as many sodium ions, right? So it should be 443 millimoles of sodium ions. That's my mistake. So it's 2.08. It's twice that. Here. Okay. I'd like to say I did that on purpose for a teaching moment, but I can't. I made a mistake and tried to recover somehow. Don't do as I do. do as I say. Let's see. How about 49? Let's see if we can get anything from that one besides mistakes. An unknown diprotic acid requires this many mils of this sodium hydroxide to completely neutralize a 0.580 sample. Calculate the approximate molar mass of the acid. Okay. So let's work it backwards. A molar mass of the acid. What do we need for the molar mass? I abbreviate that molecular weight because MM just didn't look right. Molecular weight, we need the grams mass per moles of the acid. Okay. So what do we have so far? 0.58 gram sample. Yep, we got that. 0.580 grams. Now we need moles of the acid. So we're going to have to go to a balanced equation. This unknown diprotic acid, H2 something. Okay, it doesn't matter what that is. I'll show you why. This is aqueous, and then we're going to neutralize it with sodium hydroxide. All right, so what are we going to get? We're going to get sodium plus X, which is in solution, plus water. And by definition, this is a salt. Okay, so let's see, are we balanced? No, we've got two hydrogens, we need two hydroxyls, right, to make two waters. That's the key for this one, writing this one correctly. So what does that mean? 0.11 molar, 0.111 molar sodium hydroxide, and 44.39 milliliters. Right? So how many moles of sodium hydroxide? Let's see, 0.111 and 44.39 times is 4.927 millimoles of sodium hydroxide. But we need how many millimoles of hydroxide is that? This is the compound, so we actually have 2 times that. No. 9.85 millimoles of hydroxide ions. Well, actually, we don't need to do that. Now, come to think of it. This is the millimoles of that one. Let's just use coefficients. Get rid of the sodium hydroxide and leave you with the acid. So it's 2 here and 1 there. Yeah. Divide 2 into that. 2.46 millimoles. 2.46 millimoles of the acid, which is what in moles? We'll just take this milli, put it out here in the -3, right? So 2.46 times 10 to the -3 divided into 0.580. 0.580, we'll divide into that. And I get 235, that's probably close enough, 235 grams per mole. Right here. Okay. All right. Is that 49? Yep. I think 49. And then 52, does 52 give us anything new? Which of the following does nitrogen have an oxidation state of +4? Okay, we can do this one pretty quick. Oxidation state. So oxygen is -2, right? Well, I better write it bigger. HNO3. This is -2. This is +1. So that's -6, and a +1 is a -5, which means nitrogen has to be a +5. So that's not it. NO2. NO2. This is -2, so that's -4 +1. Yep. That's the one. Since we don't have any one of the above, two of the above, or yada, 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 those odd ones, then once you find the right one, that's it, you're done. Okay, 52. Skip down to 60. There we go. Which of the following are oxidation reduction reactions? Okay. Let's see if we can find any rules of thumb in here. There's a copper element and copper compound. That's one. Let's see. The rest of them we're going to have to calculate. So this phosphorus, I can tell you this one is. How do I know? Well, one thing, that chlorine is an element here and it's in that compound there. But also, you can look at the phosphorus. If chlorine is -1, 3 minuses against 1 phosphorus is +3. 5 minuses against 1 phosphorus is +5. So we know that one is also. How about this one? Let's see. This carbon is a +4, right? 2 times -2 is -4. That has to be a +4. How about this carbon? Well, that CO3 is 2-. So that means this 2- for this oxygen is -6, but we have to hold out 2 minuses, so it's -4 that has to be balanced. So the carbon didn't change. Lithium. Lithium's always +1. It's not going to change. Oxygen's -2, -2, -2, -2. Hydrogen is +1. Nothing changed there. So 3 is not. How about this one? Iron. What's that one? +2. How about this one? -1 times 2. This one's +2. Okay. So that one isn't working. Hydroxyls, they stay the same on both sides. Sodium stays the same on both sides. Chloride stays the same. So 4 is not redox either. So it's only 1 and 2. You can probably figure that one quicker in your head on an exam. But I'm explaining details here. Let's see, skip down to, let's see, 77. We got 10 minutes. Let's see, do I have time to do 77 and 78? Maybe. 77. Okay. Balance the following equation. This one's fun. Why? Because of that compound.
Yeah.
You know what that is? It looks like this. And then it has 1, 2, 3, 4, 5 hydrogens. Right? How about the nitrates? Go on this side.
Should know what.
Okay, what would this be if there were hydroxyls here? Glycerol, right? That's the foundation for making true fats in our bodies, or in any animal body, right? In any plant, actually. You just take nitroglycerin, right?
Really expensive.
Yeah, it's kind of sensitive. Doesn't take too well to insults. Okay, so when nitroglycerin decomposes very rapidly, it makes this gas, and so enough heat to make that gas and that gas. So that's where its explosive force comes from. It makes what? Out of 1 mole of this, you get 1. Oh, we got to balance it first. Maybe we'd be better off with the next one. Yeah. I'll just make a point of this one. For every 4 moles of this one, you get 6, 18, 28, 29 moles. So the ratio is 4 moles of this as a liquid, and 19 moles of that as a gas. And that's a massive increase in volume, plus a little heat. So that's where the explosive force of nitroglycerin comes from. And it was very dangerous to handle as a liquid until Alfred Nobel solved the problem. He took this carbonate-rich material that was derived from ancient beds of diatoms. Actually, it wasn't all carbonate, it was silicate too. Diatoms are a combination. Called Kieselguhr. And he mixed this stuff with Kieselguhr, and he found that you could smack it with a hammer and it wouldn't go off. So it stabilized it. The problem is, over time, it tends to sweat. So a stick of dynamite in an old box, if you open it up without knowing what you're getting into and you see a stick of dynamite, it's got little beads of liquid on it. Back off very slowly. Vacate the building and put up a sign until the pros come in and dispose of it, because that stuff is ready to go. It sweats. Okay, let's go to the next one and balance this one. And then we'll be done. Ki plus nitric acid yields KNO3 plus nitrogen monoxide plus iodine plus water. There we go. Okay, why do I think it needs to be redox? Because this is 0, this is -1. We do have a redox reaction here. Potassium didn't change. Hydrogens don't change. One of these nitrogens did change, because this is, let's see, +1, -2, so -6, +1, 5, +5. This nitrogen is +2. But this one is still +5. Okay, so we've got our oxidation and reduction going here. This iodine had to lose. We had a loss of 1 electron per iodine, correct? And this one, we went from nitrogen here over to this nitrogen. And there we gained 3 electrons per nitrogen. Gain 3 electrons per nitrogen. Okay? In order to balance the iodines, we need 2 of these. So that would be ×2. Well, actually, okay, this is intermediate step. 2 electrons for the iodines but 3 electrons for the nitrogens. So how do you get 3 to balance 2? Cross multiply. So we're going to multiply this one times 3 and this one times 2. So multiplying this one times 3 puts a 3 here. And a 3 times this one here makes it 6. So now we have 6 electrons. We need 6 electrons up here. So how did we get 2 of these? Well, we needed 2 of these nitrogens, right, to go to 2 nitrogens there. Yeah, equals 6 electrons. Now we've got a new starting point. The electrons are balanced, and we'll go from here to balance the rest of the way. Okay, this is going to be 6. Yeah, I'm going over. There we go. Now we got a new starting point. Potassium, iodine, hydrogen, nitrogen, oxygen. So now we're starting with 6 potassium, 6 iodine, 2 hydrogen, 2 nitrogen, and 6 oxygen. This side we're starting with 1 potassium, 1, 2, 3 nitrogens, 3, 4, 5, 6 oxygens, and iodines, 6 iodines, hydrogens. Only 2, right? Now, sometimes I just count up the number of atoms to be sure I've made my tally correct. Like 1, 2, 3, 6 is 9, 10, 11, 12, 13, 16, 17, 18, 12, and 6 is 18. Okay, let's see, 6, 12, 13, 14, 15, 16, and 6 is 22. So 18, 20, 22. Okay, so my initial count is good. All right, now it should be simpler to balance. We need 6 potassiums on this side. Okay, 6 potassiums. So what does that do to this one? 6 nitrogens, 8 nitrogens. Right? 2 plus 6. 18 oxygens, 20 oxygens, 21 oxygens. Okay. Iodines are good so far. 2 hydrogens. 8 nitrogens. We need 8 nitrogens on this side. Unfortunately, it comes from one place. So in order to get 8 nitrogens on this side, we have to use 8 here. Like 8 nitrogens. That makes 8 hydrogens and 24 oxygens, correct? Okay. Now 6, 6. We got hydrogens, nitrogens, oxygens left. Hydrogens, where do hydrogens occur? Right here. So we need 4 of these. So that makes 8 hydrogens and 4 oxygens, 4, 5, 6, 6, and 18 is 24, right? Oh, I forgot to do nitrogens over here. 8. 6, 6, 8, 8, 24. There we go. So that's one that I could have stood there all day long and never got it balanced without going the oxidation reduction route first. Get those electrons balanced, then the rest of it falls into place. Okay. We might need a break. before we get started on the lab